So in the previous video we looked at the mass-energy and energy-momentum relationships, and now we're just going to develop things a little further, and we're going to think about the conservation of energy and momentum. So if we think about a system of n particles, if there are no external forces on the system, so it's a closed system, then the energy and momentum of the n particles should be a conserved quantity. Okay, so the total energy is the sum of the energy of all of the particles individually. So the ith particle, and we have n particles, so this sum runs from 1 to n. Okay, that's the total energy. We also have that the total momentum, so from the first particle to the nth particle, and this is the 3-vector momentum, p. Okay, px, py, pz. It's 3 momentum. So these two quantities should be conserved if it's a closed system. But remember, we have our 4 momentum, p mu, which is defined as the energy of a particle over c. So this is a 4-vector. So in the time-like first component, we have E over c. And then in the 1, 2, 3 components, we have the momentum p, the 3-vector momentum. Okay, and we know that E equals mc squared, the relativistic mass, times c squared. So we can also write this as mc p, okay, where this is the relativistic mass. Okay, which is the rest mass times gamma. Now, if we have a system of particles with energy E that's conserved and total momentum P that's conserved, you can see that for each particle, the 4 momenta has energy in the first component, and then P in the 1, 2, 3 components. So if we think about the sum of all the 4 momenta, so this is the 4 momentum of the ith particle, and we sum over all the n particles from 1 to n. Okay, this 4 momentum will have in its first component the sum over the energies of all the ith particles from 1 to n divided by c, and then in the 1, 2, 3 components it will have the sum of the 3-vector momenta from 1 to n. Okay, so these components we know to be conserved quantities. Okay, so we have that the conservation of energy and the conservation of 3 momentum demands the conservation of 4 momenta. Okay, so 4 momentum is conserved for a system of n particles that have no external forces. Okay, so we can write the total 4 momentum, let's call it Q, and it equals the sum of all the 4 momenta of the individual particles. And it's a 4-vector. Okay, so we sum over, so I just labels the particles, it's not a coordinate index, it's just a label of our particle number, but mu is a space-time index, so we need mu on both sides. Okay, so this is the total 4 momentum, and it's a 4-vector. Okay, so momentum itself, the 4 momentum itself for each individual particle is a 4-vector. The total is a 4-vector. Okay, so this transforms. So it's a 4-vector. Okay, and that means that in a different frame, the total 4 momentum is just given in terms of the one in the other frame, the unbarred frame. We need a different index. Mu, nu, and this is our Lorentz transformation. Okay, so this is the total 4 momentum in one frame, the total 4 momentum in another. Okay, so we've got a 4-vector that's the total momentum, the total 4 momentum. If we think about the length of this, Q mu, so it's the inner product with itself. Okay, this equals, so we know what the components are. So this will be this thing times itself with a minus sign. So we get minus the sum of all the energies of all the particles divided by C, all squared. Okay, so we get 1 power from the first Q, the second power from the second Q. And then we have a plus for the 1, 2, 3 components of our metric. And we get that we have this component times itself with a plus in front. So we get sum P I from I equals 1 to n squared. Okay, and that means we take the magnitude of this total vector. Okay, and this is Q is a 4 vector, so we can call this thing A. We've summed over the space-time index, so there are no free indices left, so A is a scalar. Okay, the length of our 4 vector, as we know, is a scalar. So this quantity on the right-hand side, this is an invariant. Okay, so this quantity won't change from frame to frame. So if we think about a different frame, Q bar, then Q bar mu will give the same result. Okay, so this is just a number, you get the same number. Okay, the same scalar. Okay, so this is basically conservation of momentum, for momentum, all you need, but we can use these principles to solve some collision problems, and that's what we'll do next. Okay, so we're going to consider some general problems where we have bodies colliding, like 2 particles colliding, and something happens. Okay, maybe 2 particles emerge or different particles emerge. And we're thinking about the total for momentum, okay, which is the sum of all the for momenta for each individual particle initially, say. So let's say we have n particles initially. Okay, so we've got n particles, 1, 2, 3, 4, etc. all colliding in some way. That's initially. And then finally we have some different number of particles, for example. Okay, so something may happen that changes the particle number, or well, we'll see. We'll talk about it. So it's useful to keep in mind that we've got this energy momentum relationship. Okay, and it's that yeah. So with this we can think about Q mu, the length of our total for momentum. Okay, we wrote it down a second ago. But here we keep it general. Okay, and it will be a sum over I from 1 to n for the first Q, and let's have a sum over j from 1 to n for the second Q. Okay, and then we have p I mu, p j mu. Okay, and these i's and j's label the particles, so these are particle labels. And this mu is the space-time. It's the space-time index. Okay. Oops, this should be down below. So there's an inner product with p mu and p mu, but they're p's of different particles. It's the 4 momenta of different particles. It's the ith particle and the jth particle. Okay, so we can take out all the terms with I equals j. So this is the sum from I equals 1 to n of p I mu p I mu. Okay, so this sum splits up into terms that have I equals to j. Okay, and that's this thing. And then it has the cross terms plus the sum I not equal to j from 1 to n of p I mu p j mu. Okay, but p I mu is the length of the ith 4 momentum. So we know that p mu for any particle, okay, it's equal to minus its rest mass, let's call it m0 squared c squared. Okay, and this is the rest mass. Okay, so this sum we can write as the sum from 1 to n of minus mi squared c squared. Okay, where this is the rest mass of particle I. Okay, plus the cross terms. I not equal to j from 1 to n, p I mu p j mu. Okay, so this is what we tend to do in these problems. It's usually useful to write down the total 4 momentum. Okay, and think about then squaring that. So squaring meaning taking the inner product with itself. So finding the length of the total 4 momentum, and then using the invariant of our length of an individual 4 momentum. So the length of a 4 momentum is minus the rest mass squared c squared. Okay, so remember that E squared is m0 squared c squared plus, sorry, c to the 4 plus p squared c squared. Okay, so p mu times p mu. P mu is the product of E over C, P with itself. Okay, so I have a metric in here, minus 1, 1, 1, 1, and then an E over C, P. Okay, and that's minus E squared over C squared plus P squared. Okay, and minus E squared over C squared plus P squared is M squared C squared. So this is M squared C squared, rest mass M. Okay, so it's helpful to memorize some things, and one thing I'd burn into my mind is that the length of a 4 vector is equal to, yeah, we've got a minus here, minus m0 squared c squared. Okay. Okay, so this is general. Let's think about a problem where we apply this type of principle. Okay, we'll see it a bit more simply. Yes, so the point is that initially we've got Q mu. So after the collision, we must also have Q mu. Okay. but we may want to find the energies of these m particles. Okay, so this equals minus I equals 1 to m of the m particles in the final state, mi squared c squared. Maybe we have to call it something else. Let's call it f for the final ones, plus f g equals 1, f not equal to g, 1 to n, p f mu p g mu. Okay, and these particles m1 to mm, we've got m particles coming out. They're different from the initial particles in general. Okay, so by knowing the masses of the particles at the start of our collision and the momentum, we can work out the masses or the momenta of the particles coming out of our collision. Okay, and we're going to have a look at an example now, and hopefully this will make it a bit clearer. Okay, so let's put this into action, and let's think about a problem where we have a proton that collides with a proton that's at rest. So it's at rest. Okay, and these form the proton and the proton, but some of the initial energy of these two guys colliding can be used to create mass, okay, because mass and energy are interchangeable, remember. Okay, so we can have that we form a proton-antiproton pair. So the bar is an antiproton. Okay, and this happens because we can interchange mass and energy. Okay, so here's the question. What is the minimum energy that the first proton needs to have in order for this process to be possible? Okay, now this is special relativity, so we're free to change frames and to choose a frame that's most convenient to us. And we want to exploit the fact that form momentum is conserved. So the initial form momentum, total form momentum, qi mu, equals the total final form momentum, qf mu, which is the form momentum of all these guys. And the initial one is of the two initial protons. Okay, and yeah, let me just say that the rest mass of all of these protons and antiproton is mp. Okay, so that's the rest mass. Okay, so it turns out that in these collision type problems, there is a very helpful frame, and it's the center of momentum frame. And it's defined as the frame in which the sum of all the three momenta of all the n particles is 0. Okay, and it's 0 with a vector. Okay, so it's 0 in all components, x, y, and z. So we can work in the center of momentum frame. We have that q, so the initial form momentum equals the final form momentum. Okay, but we know that if we change frames, the length of our four vectors is unchanged. So let's call this q mu. So the length q mu is an invariant quantity. Okay. So it takes, so the inner product, so the length of q in any frame will be the same. Okay, so it's invariant. Okay, so using this, we can solve this problem rather straightforwardly if we move to this center of momentum frame. Okay, so let's go to the center of momentum frame. and the total form momentum in the center of momentum frame. So our form momentum is the sum of EI over C for all n particles, PI. Okay, and in the center of momentum frame, sorry, there's a sum over I from 1 to n. In the center of momentum frame, this PI sum just goes to 0. So we've got EI over C, I equals 1 to n, 0. Okay, and because this is 0, this means we can calculate the length of this guy easily. Okay, so just let me write that again. We've got Q mu center of mass, Q mu center of mass. Probably put it this way, right? Center of mass mu equals the sum, and there should be a minus here, sorry, minus the sum from 1 to n of all the energies in the center of mass frame, divided by c squared. Okay, and we can write this as minus E center of mass squared divided by c squared. Okay, where E center of mass is just the sum of the EI stars. Okay, so the question asks what's the minimum energy for this process to be possible? So what does that mean? For the process to be possible, we have to create 4 particles of rest mass mp. So we need at least 4 mp c squared of energy, because that will allow us to create the masses, and it'll allow us to create the masses, but we'll have nothing left over for kinetic energy. So 4 masses will be created, but they'll have 0 kinetic energy. So the minimum energy, okay, is equal to minus 4 mp c squared divided by c squared. Okay, which is equal to minus 16 mp c squared. So this is the minimum. Okay, so we have that Q mu in the center of mass frame, Q mu in the center of mass frame equals minus 16 mp squared c squared. Sorry, there's a square here, so this should be squared. Okay. But we know that the length of this total form momentum is an invariant quantity. So this must also equal Q mu in the lab, Q mu in the lab frame. Okay, and Q mu in the lab frame contains the energy E1 that we want. Okay, so let's make that more explicit. So Q mu in the lab frame is P1 mu plus P2 mu, where P1 mu is the form momentum of this thing in the lab frame, and P2 mu is the form momentum of this thing in the lab frame. Okay, so this inner product is equal to P1 mu plus P2 mu P2 mu plus the cross terms 2 P1 mu P2 mu. Okay, and we know from the length, we know that the length of our 4 momentum is just minus mp squared c squared. So these give us minus mp squared c squared. And all we have to do is work out what 2 P1 mu P2 mu is. Okay, so we've got, let me make some space. Okay, so we find that from just the invariance of the length of our total form momentum, that minus 16 mp c squared equals minus 2 mp squared c squared, 1, 2, plus 2 P1 mu P2 mu. Okay, But in the lab frame, P1 mu equals E1 mu over C, P1. And P2 mu is the form momentum of our second proton. But it's at rest, so its energy is just the rest mass, mpc, and it's got zero momentum. So P1, P2 is just minus 2 E1 over C times mpc. Okay, so this tells us that minus 14 mp squared c squared equals minus 2 E1 times mp. Or E1, the energy, the minimum energy required, so that's the answer to the question, is 7 mp c squared. Okay, and energy is mc squared, so we've got the dimensions okay. So that's the minimum energy, and that means the minimum kinetic energy, T, is E minus the rest mass energy, mp c squared, which is 6 mp c squared. So this is the minimum kinetic energy. Okay, so if you have a proton that has less kinetic energy than 6 mp c squared, this process will not be possible, because you won't have enough energy even to create the four masses. Okay, so this was an example where we used conservation of form momentum and we changed frames. So we're using the concept that the form momentum is conserved, so the initial form momentum, total form momentum, equals the final total form momentum, and that the length of a form momentum is an invariant quantity. Okay, so we can change frames also. So we brought in the concept of this center of momentum frame. Okay, so this is not the most straightforward question, but I wanted to go through it. But in the notes there's a simpler question, or simpler problem, where you have a mass m and it decays into two other particles. So it's at rest and it decays into two other particles, m1 and m2. Okay, so work through that in your notes. And I also consider the case of electron-positron annihilation, where you have an electron and a positron, and when they annihilate you get two gamma rays that come out back to back and with equal energy if you're in the center of mass frame, center of momentum frame. Okay, so in my research I study this process and I think about what happens when an electron in an atom, okay, here's a nucleus and here's your electrons in the atom. When a positron comes in and annihilates with one of the atomic electrons, then you get two gamma rays coming out. So you have a positron coming in, it annihilates with one of the electrons. They disappear from the universe completely and you get two gamma rays, gamma 1 and gamma 2. Okay, but in the center of mass, center of momentum frame, the two gammas come out back to back and with equal energies. But in the lab frame, which is reality, okay, the gamma rays have, they emerge at a slight angle and they're Doppler shifted in energy. Okay,